Hey everybody, I want to clean up a few things regarding this last part of chapter 27, specifically some of the applications of the force law that we derived in another video. That basically the force is given by the cross product of the charge Q times the velocity vector V crossed with the magnetic field B. So let's let you look at my other camera view real quick. So some of the ramifications are kind of interesting, and they actually give us a lot of applications. We can use them, for instance, to determine the strength of a magnetic field. We can use them to actually determine current going through a wire, all sorts of good stuff. So first off, remember the force is given by Q V cross B, where B is the magnetic field strength measured in Tesla. Q is the charge of the actual particle moving with velocity v, and then of course v is the velocity. I'm trying to get that better focus. It doesn't look like it's doing a very good job. So that's Q v cross b. So what that means is, if you remember, when you multiply a vector times a scalar, for instance, if you have a vector a that looks like this, and if you multiply it by a number, let's say 2, then you're going to get a vector that's twice as long as this one, and it'll be called vector 2a. So just like that, if you multiply v by a charge q, if the number is bigger than 1, it'll get longer. If the number is smaller than 1, it'll get shorter. If the number is negative, though, it'll actually turn around. So for instance, negative a vector would in fact be this. So that's sort of the key to figuring all this out, is you've got to realize what happens when you multiply a scalar times a vector. Now, also, you got to remember that cross products are behaving sort of a weird way. So for instance, if you have a vector, let's say this is the vector QV. Okay, so I've already taken the time to multiply Q times the velocity, so it actually has units of coulombs meters per second. And then let's say we put it tail to tail with the vector B, then we have to lay our right hand, say our pinky, along QV, and then our hand can rotate any direction we want it to, but we got to choose a direction where our fingers can easily curl towards B through the shortest angle. Obviously, you can't go backwards like that to the other angle. So when I do that, I curl them towards this way, and my thumb points straight up, and that is the result. Is basically, anytime you do a cross product of two vectors, you get a vector that's mutually perpendicular to the original two. So it's this one curled into this one gives you a vector pointing out of the board, okay, or out of the piece of paper in this case. Don't forget, and do it with your left hand, because you're writing with your right hand. You've got to actually stop and use your right hand, or you'll get the opposite result. So with that in mind, we can figure out a few things. For instance, if you actually send an electron, say, there's an E minus, if we send an electron through a little hole, and then through a directly aligned hole where the magnetic field is actually pointing into the paper, say, and it's uniform, then what will happen, since this electron, V is this way, but it's an electron, so QV will actually point this way. So QV points that way, and the vectors are pointing down into the page, so I go QV, and you see my hand points to my thumb points to the downward direction. So the force due to magnetism would actually be in the downward direction. So this is the F due to B, which I'll call F sub B. Now, if that's the case, then this electron is going to fly through here and just hit down here, and it won't make it through the hole. But if I do make this hole fairly narrow, I can actually use this as what we call a velocity selector. So for instance, I can apply an electric field to make it counteract the force due to the magnetic field. And then that'll, if I harmonize the electric field and the magnetic field in such a way that those two forces cancel out each other, then I will actually get the particles going straight if they have, as you'll see in a second, the right velocity. So what I need is the force due to the electric field pointing this way. And electric field vectors point in the direction that a positive charge would go. So the electric field is actually going to point downward. that means I would actually need the negative side to be down here and the positive side to be up here. So I put little negative charges along here, sort of like a capacitor, because that's really the best way for us to get a nice uniform electric field is by having a capacitor. So now if I let the net force be equal to 0, I'd say Newton's second law says the summation of forces in the y direction, I'm treating this as x and this is y, in the y direction is equal to mass times acceleration in the y direction. If I want that to actually equal 0 though, that would have caused it to go in a straight line path. Then I'd get F due to the electric field's the positive direction, and I'm going to call the magnitude of the F due to the magnetic field FB, and I put a negative on it just to show that it's in the negative direction, and I'll say that's equal to 0. That means that FE has got to equal FB for this to happen. Now FE is just equal to the electron charge times the electric field. So that, and FB, since QV points this way and B points that way, they're automatically perpendicular. So the other part that we use regarding cross product is the magnitude of F, which equals the magnitude of QV cross B, is just equal to Q times V times B times the sine of the angle between them, where the angle between them is that angle. With that, I know the angle is actually 90 degrees, sine of 90 is equal to 1, so I just get the electron charge times the velocity of the electron times the magnetic field. So that's the condition for these electrons to go straight through from this little hole straight through to that hole. You can cancel out E on both sides, and you'll see that the velocity has to equal the electric field divided by the magnetic field. That is a velocity selector. You can even allow a certain error in the electric field, a certain error in the size of the magnetic field, and see how wide that would make this hole be before it would actually allow the particle to make it through, all sorts of stuff like that. But generally, that's the rule. You just have to set the velocity equal to the electric field divided by the magnetic field. Another thing you can do with this law is you can actually use it to choose out masses, for instance. If you now take this velocity selector, which is basically a parallel plate capacitor, remember, with positive charges on this side and negative charges on this side, and it's got a little box here with a little hole and another plate here with a little hole. Now, if I use that and have magnetic fields going into the page like this, and I'll let an electron in that way, then what I'll end up getting is electrons coming out with exactly that speed. Assuming I make the slit narrow enough, I'll get the electrons coming in with the speed equal to the electric field by the capacitor divided by the magnetic field that it goes through. And then if I subject it to, say, another magnetic field, let's say another one going into the screen, into the page, what will happen is this electron will be going this way, the V is that way, so QV, which is the electron charge, which is negative, will be pointing this way. Again, QV cross B gives me a force pointing this way. So the particle will actually tend to move down this way a little bit. So now QV is this way, but QV cross B gives me a force that way. So it deviates more, and I think you can see eventually what's going to happen is the particle will come back into a circle. So if you have another opening here, say, and you send the mess of particles, let's say they're not all electrons. Some are electrons, some are atoms missing electrons, some are atoms with extra electrons. Each one will have a different mass. And what we'll have is a velocity coming in that causes a magnetic force. That magnetic force is equal to the charge that it has times the velocity that it has crossed with B. And that's going to tend to cause an acceleration. And according to Newton's second law, the summation of forces is equal to mass times acceleration in the direction that we're talking about, which is acceleration perpendicular to the velocity. We'll have that's equal to the mass of the particle times the acceleration, which is that of a circle. So we'll say v squared over r. And I'm going to just set that in magnitude because, again, we've got everything equal and in perpendicular direction, so we don't have to actually worry too much about the angles and all that good stuff. So I'm going to have q v b, again, sine of 90 degrees is 1, is equal to the mass times v squared over the radius of the circle, which is this distance right here. Now, I want that to be exactly that distance, so I can now use the velocity that I have here. I have a new magnetic field, which I'll call B prime, because this is not the one that created the velocity. So with that in mind, I can say cancel out this velocity with that velocity, and I'll end up getting a radius equal to m times the velocity over the charge times the magnetic field. So every particle that hits at this distance r out will actually have the same mass to charge ratio, if you will, because it's dictated by the velocity, which the velocity selector already chose, and it's also dictated by the magnetic field strength, which is set. So that can be used as a mass selector. Now, basically, almost everything's going to have a charge of 1 electron charge or 2 electron charge, so it's almost always just going to be E here, not Q. That's because atoms normally ionize themselves by losing an electron or gaining an electron, so they'll be up a charge, positive if they lost an electron, or down a negative charge to a negative charge if they gained an electron. So there's a mass selector, which is sort of the principle of what we call a mass spectrometer. So the mass selector is basically part of a mass spectrometer. Now, the final thing I want to talk about is something called the Hall effect. And the Hall effect is kind of neat because it allows us once and for all to see that the electric field, or excuse me, that the carriers of current, whether they're positive or negative, really matters, but pretty much only in this experiment. So we've been treating this conventional current as if positive charges are moving in the direction of current. So we'll say current I is this way. This is an actual wire here. And if it's a wire, we can submerge it, for instance, in a uniform magnetic field. Say, let it go between 2 poles of a magnet, whose strength we actually know. And what I'll do is I'll say the magnetic field strength is B, and it points into the page again. Okay. So this is our uniform magnetic field pointing into the page, and we're going to let the charge carriers carrying the current I come in, and we're going to see what happens. So first, let's imagine conventional current, which is that there's positive charges moving from left to right. So if we in fact have a positive charge Q, so let's say plus Q, then QV is actually this way. So if that's the case, then QV crossed with B gives me a force upward. So we're actually going to have an accumulation of extra charges, plus, 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 all on the side, because all these positive charges are going to tend to fall that way. Okay. Now, what happens if it's actually negative charges? So if we had a negative Q, in other words, like electrons, then QV would actually point this way. Okay, so now QV points that way, cross it with B, that means I got to put my hand this way, and I see it's pointing down. So that would actually cause, in fact, negative charges to accumulate. So the negative charge, or a current going this way, is positive charges going this way, or negative charges, excuse me, going this way. And then, I said this wrong here, then QV is that way for a negative charge. Sorry about that, I drew this wrong. So if it's a negative charge is carrying it, then the negative charges would actually have to move this way, so that QV is the negative of V times Q. So QV would actually be this way. And in this case, you get QV cross B. And again, you'd get, in this case, negative charges piling up here. So if the charges are positive, the positive charges go up. And this will have a higher voltage than this side. If the charges are negative, on the other hand, then the negative charges will move up, and you will have a negative charge this way, but down here you'll have a positive voltage. So you can actually determine this, and lo and behold, this is the very experiment. It's called the Hall effect. It's called the Hall effect, and it is actually how we determined that it was in fact electrons carrying current. So the Hall effect showed that what really will happen is negative charges pile up on this side, so you get basically an equivalent amount of charges that reaches equilibrium. So once you get enough negatives over here, then you've essentially got a electric field that points this way. This is called the Hall electric field, pointing upward. That Hall electric field, once it gets the right size, then it can exactly cancel out the force due to the magnetic field. And if that's the case, then they'll stop piling up there, and the electrons, sort of like in the velocity selector case, will continue to go through unmolested. So they'll move on without changing paths at all. We could actually measure what that potential difference is, that voltage. It's called the Hall voltage, and they usually use the symbol E sub H. And if we sort of imagine it's going to be a uniform electric field, it's not unreasonable to think that it's the electric field due to a capacitor, which is uniform. So you just say it's going to be the electric field strength times the width of the wire, D. So what we'd say is E Hall times D. That's the voltage difference. When you have that, then you can say, well, I know that voltage difference, E Hall, is going to be equal to basically the electric field strength, because that's what this is. That's got to match the actual the magnetic force. So we say EH is going to equal, let's say, our Q times EH. That's the actual force. So we'll say Q times EH is actually equal to Q times the velocity times the magnetic field. Again, everything's perpendicular here. So the Q's cancel out. We end up getting EH has got to E equal to the drift velocity, which is what this velocity VD is here, times the magnetic field. So we can measure, if we actually measure the Hall voltage, we will get basically the drift velocity times the magnetic field strength times the thickness or diameter of the wire. So that's really the Hall effect. With that in mind, we could measure this. That's experimentally easily determined. We just put a voltmeter on one side with the positives up here, say, and the negatives over here. If that's the case, it'll build up actually negative charges over here, so it'll read a negative number. But either way, you can get the number. So that's a known. If you know the strength of the magnetic field, you can call that a known. You know the diameter of the wire, you can call that a known. That gets you a way to determine the drift velocity. So we can actually determine what is the drift velocity. We already knew that the drift velocity could be calculated from a theoretical standpoint as the drift velocity is just equal to the number of charge carriers times the electric field divided by the strength. So we knew the drift velocity is actually supposed to equal sorry about that. The drift velocity is actually supposed to be equal to the current I. Sorry, I'm referring to my notes. It's supposed to be equal to the current I divided by the area, that's the current density in other words, and then divide that by the number of charge carriers, we call that N, and then the actual amount of the charge, and that's the letter E, 1.602 times 10 to the negative 19th. So the drift velocity is I over N times A, the cross-sectional area of the wire, times the electric charge. So once we know that, we can use that to check what our N is, and that's the number of charge carriers per cubic meter, which is related to the density and the molecular weight of the material. And lo and behold, that gives us a good check on not only this formula, but what is the total number of charge carriers, say, in copper. So that's how the Hall effect can be used. Now, if you also, let's say you've already settled the science of wondering what the charge carriers are or what the velocity, drift velocity is, you can then turn this on its head, use a very precise piece of wire with a very precise amount of current going through it, and use that to detect the actual magnetic field strength. That is one of the ways we can detect the strength of a magnetic field. So the Hall effect gives you basically an ability to determine the number of charge carriers per cubic meter in a particular metal. It gives you a way to determine the velocity, the drift velocity of the charge carriers. It showed us that the electrons were actually the charge carriers. And if you know everything else, you can even use it to make a device to, or a gaussmeter, if you will, to measure the field strength, the magnetic field strength. So with that, we have yet another application. I've already showed you that you can use it as a velocity selector using QV cross B and the electric field. So that basic law of force related to magnetic field and charge and velocity allows us to make a velocity selector, and then we can use that to make a mass selector, which is in fact a mass spectrometer. I think with that in mind, you should have enough to see all the cool applications and solve the rest of the problems that you'll see in examples in your textbook or whatnot.